Hi and welcome to my channel. Today I'd like to talk about transmission lines and the telegrapher's equations. The reason I'm doing this video is because usually the first lesson on transmission lines starts with capacitors and inductors connected in some cascade, and it really doesn't, at least in my opinion, describe what the transmission line is and what's happening there. I'm going to take a slightly different approach using Maxwell's equations, but I'll show the connection between all the inductances and the capacitances so you get the general picture. So let's begin, but before we begin, you should know and have some background on Maxwell's equations, preferably in the differential forms, but it's good also to have the knowledge in the integral form of these equations. You should know what is a capacitance and inductance, and it's good that you've seen the wave equation in its standard form, which does require some knowledge in partial differential equations. So let's start by taking the simplest possible transmission line. The geometry is very simple and the equation will also be as simple as possible. The transmission line we will discuss is a thin coaxial transmission line. You have an inner conductor and an outer conductor in a concentric cylindrical geometry. We assume the transmission line extends to infinity in the z direction. The distance between the conductors is very small compared to the radius of the conductor, and we'll denote this small distance, the gap, with the letter G. The radius of the inner conductor will be denoted by R. We're going to inject current in the inner conductor, which is the positive side, and pull the current out from the outer conductor. If we zoom in the transmission line, we can approximate this small section as two planes parallel to each other with a small gap. Taking the z-axis as what will be the propagation wave, the x-axis is parallel to the planes, and the y-axis is perpendicular to the planes as shown in the picture. The y-axis is of course the radial. If you look at the big circles, it's the radial direction, and x is the tangential direction. Let's try to calculate the capacitance and inductance over a small segment z in the z direction of this transmission line. The capacitance is fairly easy to calculate. You take the small segment dz. The area of this small segment is dz times the length of the circumference. So the capacitance is just this area over the gap thickness g times epsilon 0. Substituting for the area, we get this expression in units of farads, of course. But if we want to get rid of this dz, which is the small segment of the transmission line, we will actually calculate the capacitance per unit length. In our case, the capacitance per unit length is in farads per meter because we are working in the MKS units. We will denote this by C hat, which is epsilon 0 times 2 pi r over g. Now for the inductance, I'll quote a well-known formula, but don't be afraid, we'll derive it in the next slide. This is the standard formula for induction of a coaxial line. The ln, of course, is the natural logarithm, and if you can approximate the natural log for a number that's close to 1, 1 plus a small value, the log of that number is the added value to 1. So in our case, g is much smaller than r, so we can use this approximation and approximate the natural log of 1 plus g over r by g over r. So we arrive at the formula for the inductance in Henry. And if you calculate the inductance per unit length, you get this formula where mu0 is the vacuum permeability, and of course you have the radius and the gap. So let's derive the formula for inductance in our case directly. We're using Ampere's law. Remember that this is a big circle, so going around the circle you get the magnetic field times the circumference is equal to the total current in the conductor times the vacuum permittivity, and then we get that the magnetic field is just mu0 times I over 2 pi r, and of course the electric field is 0. The flux is given by the gap times dz, which is the area over which the field is going through, times the actual field, which would take from here. So to get the inductance, we need to use the formula that the flux phi is L times I. And then we get again the same formula, L equals mu0 times a small element over 2 pi r times g. Okay, let's look again what the directions of the magnetic and electric fields are. The electric field is shown in blue and the magnetic field is shown in green. The electric field is of course in the direction from the inner conductor to the outer conductor, where we drive the current into the transmission line and towards the lower voltage. So you see the arrows going downwards, which is the negative y direction. The direction of the magnetic field is going around the circle because we're driving current into the inner conductor. So using the right-hand rule, the magnetic field is going around the circle in the clockwise direction. Some things to note before we continue: the electric field is not changing in the tangential direction because we have the circular symmetry. So everywhere it's from the inner conductor pointing towards the outer conductor. It doesn't change along the circle because of this symmetry. The same thing goes for the magnetic field. We are also chose the gap to be very small, so there is no place for change in this small gap. The field is constant throughout the gap. We can assume that the electric and magnetic field do not change or in the y direction. Also in the x direction, the electric field is 0 because we have a perfect conductor, and these lines are the lines of equal potential, so it doesn't change along this axis. And by using the symmetry of the current, which is along the z direction, the y component, which is the radial component of the magnetic field, is also 0. So we're actually left with very few terms in the Maxwell equation. The only components of the field which are non-zero is the y component of the electric field and the x component of the magnetic field. So this is the full-blown Maxwell's equation. Now we'll start the analysis and see they're not as scary as they seem. Taking the curl of B and just remembering that many terms cancel, we are left with only the term in the left hand side in the green box. The derivative of the x component of B with respect to the propagation direction z. And if we look on the other side of the equation, because we have no currents running inside the gap, we have that it's equal to the y components of this side of the equation, the electrical field side. which is the y component of the derivative of the electrical field times mu 0 epsilon 0. Doing the same for Faraday's law, we have that the curl of E equals minus dB over dt. Again, many terms are 0, and we're left with only this term in the green box. We again got another simple equation that the derivative of the y component of the y component with respect to z is the equal to derivative of the x component of b with respect to time. So we finally arrive at two equations, and in order to get one equation from them and to solve them, we do a standard thing. We take the derivative with respect to z to the left equation, and the derivative with respect to t to the right equation. And what this will give us is that the terms would be equal, and then we can solve for b. So we get that the z derivative and the t derivative, and notice that we have the same term on both sides except for a constant factor. So we get this nice little equation for the x component of b. If you haven't seen this type of equation, it's called the wave equation, and actually it's in its standardized form for the x component of the B field, the magnetic field. In the wave equation, the second derivative with respect to propagation direction is equal to some constant, which I denote 1 over v squared, times the second derivative with respect to time. That's the standard form of the wave equation. This v is actually the velocity of the wave, and if we compare the two equations for bx and for a, we see that the velocity of the waves is related to epsilon 0 and mu 0 by the following relation. The square root of 1 over epsilon 0 mu 0 is the velocity. Now, let's try to go back and see how the voltages and currents are related to the electric and magnetic field. The electric field is, of course, related to the voltage. Very simply, it's a capacitor, so the total voltage is the sum of the electric field from the plus terminal to the minus terminal, and of course, since the field is constant, it's just the gap times the electrical field strength. The sign here is because the field is going in the minus y direction and the voltage is positive, so we have this little minus sign. For the magnetic field, we're using Ampere's law, and we have this integral around the big circle. This integral is 2 pi r times the x component of the field, and using Ampere's law, we know that this is the actual current that's running in the inner conductor. So what we got is some conversion factor, a rather simple one, between the voltage and the electric field, and another conversion factor between the current and the magnetic field. These conversion factors are what relates the physics fields, E and B, to the actual electrical engineering voltages and currents, V and I. So well, let's do these equations again, but this time let's work with voltages and currents. The change with respect to Z of the voltage is related, as we've seen, to the change with respect to Z of the Y component of the electrical field, and this is, of course, as we've seen, related to the change in time of the X component of the magnetic field. Remembering that the magnetic field is related to the current with a conversion factor, we get that the change in voltage with respect to propagation direction is negative the inductance per unit length times the derivative of current with respect to time. Now we have the second equation, that the derivative of the current with respect to propagation z. We use the same equation between the current and the magnetic field and the same connection. And using the relation between the magnetic and the electric field that we got before from the Maxwell equation, we do some massage to the equation and get that the change in the current with respect to propagation direction is negative the capacitance per unit length times the change in voltage with respect to time. Using this and just displaying it more clearly, we get that the derivative of the voltage with respect to propagation direction is minus the inductance per unit length times the derivative of the current with respect to time. This is the first telegrapher equation, and now we have also the second equation from the second row. So we just got both telegrapher's equations from Maxwell's equations. When you have a general transmission line, I've just drawn another classical transmission lines with two wires. But here the field is not uniform between the conductors. The magnetic field is also changing over space, so it becomes a more complicated problem. But you can use the same rules. You just calculate the magnetic field as an integral of the current and the voltage as the integral of the electrical field between the two conductors. Once you calculate these, you're actually calculating the capacitance and the inductance between the two line conductors. Namely, you recalculate the conversion factors between the fields and currents and voltages. However, you get the same telegraphic equations with different values for the capacitance and inductance, which depend on the geometry and of course on the permeability of the medium. In the next video, we'll discuss the solution for the telegrapher's equations and more concepts such as impedance, wave propagation, and reflection. Thanks for watching.